should be coming on soon. Okay, just got the, and we are recording, the one minor kind of announcement. It affects office hours. I had a doctor's appointment yesterday, so it wiped out my trig class, and also really late, and it wiped out 45 minutes of my physical science class, but we kind of made that up yesterday. But the that trig class I missed tomorrow, unless the class tells me otherwise, but tomorrow I'm planning to do a double class, so 9:30 to 10:45 and then 10:45 to 12. So my office hours, which are normally on Tuesday, Thursday, 10:45 to 12:30, will only be 12 to 12:30, so greatly reduced office hours tomorrow. But hopefully that'll get me caught up a little bit, get back to whatever normal is. Now, if they can't do it tomorrow and can do it Tuesday, then I'll put it off and do it Tuesday. I mean, it doesn't have to be done right away, but I prefer to get it done as soon as possible so I don't forget it. Okay. Any questions on anything we've done up until now? Okay. Forgot to open the graph paper. I mean the clean paper, clean sheet, PowerPoint. I need something to write on. And see, the other package we used to use, Integrity, had that as an option. I could pick clean paper, white lined paper, graph paper, a variety of things, and it was all in the package. This one I have to export it from outside, and it's having trouble opening PowerPoint. I mean, it's a huge file, 3 slides, okay? One's graph, and 2 are white. I do not like I do not like Microsoft products, period. But anyway, one of these days it will open. I should have had this open before. I forgot about it. It's such a big file, I can see why it's taking so long to open. Word. My work study sheet had named it graph paper PowerPoint. Graph paper, yeah, graph PowerPoint, sorry. Where I use the white a lot more than I do the graph. So I had them put a white page in too, and then put in the second. Okay. I think finally we're ready to go. We'll start off. Okay. It is so slow. There we go. We finally are here. All right. If no questions, I think we're at the top of page 16. Okay. Example 4. You got your book. So I see no, well, let's see. Do any of the people in the class not have books? They might do, so I better write these down. Determine whether each of these matrices are in row echelon form. Can you remind me what row echelon form is? Say again.
The numbers under those are zeros.
Zeros. And the one other thing is the step down. Okay, the leading one, step down. Okay, and one other thing, any rows that are all zeros are always at the bottom. Okay. Yeah, got it. So with that in mind, let's look at these 6 matrices. Here's, well, let me get my pen back. Why it does this? Okay. The first of these, 1, 2, -1, 4. Okay. So far, could be, because it has a leading 1. 0, 1, 0, 3. Could be, its first non-zero entry is a leading 1, and it's stepping inward. And 0, 0, 1, -2. What you think? Row echelon form, yes. Okay. B. 1, 2, -1, 2. Could be. Say again? Exactly. When you see 0, 0, 0, 0, The only way this could be in row echelon form if the next row was 0, 0, 0, 0, but it's not. It's 0, 1, blah, 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 blah. That's not row echelon form. The row of all zeros must appear on the bottom. Okay, very good. C. Okay. 1, -5, 2, -1, 3. Big old matrix. Okay. 0, 0, 1. 3, -2. Does that rule it out from being row echelon form? No. Now, if any row below it had a 1 in the second column, yes, it would not be. But let's see what the others are. 0, 0, 0, 1, 4. So far, yes. So far, so good. And the final was 0, 0, 0, 0, 1. What you think? Row echelon form. You don't have to be an even stair step. It just has to be going downhill. Okay? And it is. Leading non-zero entry is a 1, and zeros below all those 1s. Now, notice this is a -5 with zeros below it. Doesn't violate anything because it's leading non-zero element is a 1, and that's the only one that's required. So no problem there. Okay. D, the fourth one, another sort of big one, is a 1, 0, 0, -1. A 0, 1, 0, 2. So far, so good. 0, 0, 1, 3. Still okay? And 0, 0, 0. What's the only two possibilities that last entry could be? 0 or 1. Yeah. This happens to be a 0, still row echelon form. Good deal. Yeah, that would be reduced row echelon form. Okay? And good observation. If this represented a system of equations in an augmented matrix, it doesn't have to. If that were the case, then this would be a reduced row echelon form. In fact, I guess it still would be considered that. But I was going to say, and this tells you that z is equal to 3. No, this may represent something completely different from a system of equations. Matrices are used for all kinds of stuff, and it doesn't have to be systems of equation. But yeah, I think that would still be classified reduced row echelon form. When we get to it, we'll see if it does fit every part of the definition. Maybe one part, that's why I'm sort of a weaseling about it. I can't remember if there's one more condition for that, but we'll see. Okay, let's do, I think I'll erase them all. I was going to just erase some. Yeah, I might just, okay. What I think I'll do is I'll leave my brackets there so I don't have to write them again. This is just the height of laziness, isn't it? Except it takes all that effort to erase. I don't know. E, 1, 2, -3, 4. So far, so good. 0, 2, 1, -1. Wipes it out right there. That 2 needs to be a 1. Of course, this would be easy to make. We're going to write the third one. 0, 0, 1, -3. It would be easy to get into row echelon form. What would you need to do? Okay. If you did that, it's a good thought. You'd wind up with a -1 here. That would make it even worse. Okay. So what would be another possibility? Can I kick you, or you're going to kick yourself? I think you'll kick yourself. Divide by 2. Divide the second row by 2. Yeah. that becomes a 1, 1 half, negative 1. 0 in front, everything's fine. Okay, good deal. We're on example 4, top of page 16, and I think Nigel's here now. Okay. When I was filling in my roll book last night, I realized how few students I teach on Mondays and Wednesdays. And it's not that, I mean, I have 4 classes, and they have 4, 4, 4, and, well, they have 4 students in each class. Though I can't tell if all of them are going to stay here, but it looks like they are. So you would say that's 16 students. Well, no, it's not, because I have I thought I had Rodney in 2 classes. I don't. Okay. I have Emmanuel in 2 classes, Marcus in 2 classes, and Nigel in 2 classes, and Jonathan in 2 classes. So it's not that many students, but it's 16 head count, but not that many students. Okay. So several of them double up. Well, that's neither here nor there. Let's look at B. Okay. No, F, sorry. Okay. 0, 1, 0, 5. Does that preclude it right there from being in row echelon form? No. Leading non-zero entry is a 1. So that you're okay. Okay, next. 0, 0, 1, 3. Does that preclude it from being in row echelon form? Nope, still okay. And finally, third row, 0, 0, 0, 0. Sure enough, that is row echelon form. And I can almost hear your question, is it reduced row echelon form? It may be, okay? You got zeros above the 1s as well. We'll have to wait till we get there and see if there are any other criteria that have to be met. I can't think that there are now. Okay. Now, we've already done the next thing here. You don't have a book yet, so okay, I'm going to write this down because this is review. It's stuff we've been doing, but it's Gaussian elimination with back substitution. Now doing it with matrices. Okay, we did it with linear equations, though we did it with matrices then, so it's nothing new. So now, when you talk about Gaussian elimination, back substitution, we are now talking about systems of equations. Okay? And with systems of equations, the first thing to do, write the augmented matrix of the system of linear equations. So this is Gauss elimination with back substitution. Write augmented matrix of the system of linear equations. Okay, so we've already done that. Okay, use elementary row operations to rewrite the matrix in an equivalent matrix in row echelon form. Use your elementary row operations, remember I call that ELOs, to rewrite the matrix in row echelon form. Okay, now to rewrite the matrix, and that will be an equivalent matrix. I like that term too. We talked about equivalent equations, equivalent matrices. Okay, third, write the system of linear equations corresponding to the matrix in row echelon form and use back substitution to find the solution. Now, we may not have done it quite following those words so you recognize it, but that's indeed what we did. Okay, so write the system. So you go back, so you start with the system of equations, write it in augmented matrix form, reduce that row echelon form, and then rewrite it as a system of equations. Okay? Corresponding to the row echelon form that you got in the step 2, can't write, and use back substitution. Okay, and generally we start from the bottom and work our way up. Okay. All right, now, I only stopped to do this just because it's sort of fun, okay? Well, let me do this one thing. Gaussian elimination with back substitution works well for solving systems of linear equations by hand or with a computer. For this algorithm, the order in which you perform the elementary row operations is important. Operate from left to right by columns. Get that first leading one wherever it's going to be, get it in place, then eliminate, the things below it. Go to the next one. Get it to be a leading one, eliminate the things below it. Do that as you go, and you'll wind up with it, especially if you're programming a computer. Now, when you're doing it by hand, if you look at that and say, wait, before I make that a leading one, I'm going to eliminate, and I can see that it's going to be quicker to do it this way than, or avoiding fractions, or, making it just easier to do. Yeah, you can weasel a little bit. But when you're programming it, you can't look at the equation. You're doing this for any equation you put in there, a system of equations, so then you have to. So that's just something I would say. To using the elementary row operations, obtain zeros in all entries directly beneath the leading ones. See, if you have those leading ones there, it's easy to eliminate the things below it. Multiply the row with the leading one by the opposite number of the thing you're trying to eliminate. Okay? And then add them together. It works. I want to say every time, and I think it does. Now, what I was going to say before, I pause here just to remind you. Papers. Linear algebra is used in GPS. If you think about it, what's required for GPS to work for you? I'm guessing all of you have used it, right? Both of you used it, right? What's required for it to work for you? Second? A network. What do you mean by that? Like what?
Internet service.
Oh, yeah. So you got to have an internet service. Absolutely. That kind of network, right? Say again? Oh, okay, got it. But if you're just trying to find where you are, okay, let's say you're lost, like maybe Marcus. No, he's not lost. Okay, he's here. Okay. It's a vague question. I'm sorry. I'll tell you what I'm fishing for. Okay, that's FIS, not PHIS. Okay. Anyway, what are you using for GPS? What is telling you where you are? And okay, satellite. So you need a satellite, right? You need 3 or more satellites. One satellite cannot tell you where you are at all. 2 satellites can narrow it down, but it still can't tell you where you are. Yes. We're on the bottom of page 16, about to go to the top of 17. You got to have at least 3 satellite signals, or else GPS is absolutely no good. Okay? So there are many satellites up there, and they are y'all familiar with the term geosynchronous orbits? What that means is they stay above the same point of the Earth all the time. Technology to do this and get them to stay right there, I mean, we've perfected it, but I mean, that's some pretty decent mathematics in that. But anyway, so your GPS is getting at least 3 signals, probably more. How do you think it's figuring out where you are? Matrices, linear algebra. Taking the 3 signals, doing calculations with them, and figuring it out. So GPS, what the brains of GPS is doing, the computer, that's doing that using linear algebra. Linear algebra applied. Okay. And it says here from at least 4 satellites to triangulate the position. 3 is the absolute minimum, but they need the 4th one because you have to have a time component in it too. So it's pretty interesting. So if that's something of interest to you, GPS, how it works, how you apply linear algebra with it, that could be a potential paper topic. All right, let's move on to example 5, top of page 17. Okay? Solve the system of equations. x2 plus x3 minus 2x4 is equal to negative 3. x1 plus 2x2 minus x3 is equal to 2. 2x1 plus 4x2 plus x3 minus 3x4 is equal to negative 2. And x1 minus 4x2 minus 7x3 minus x4 is equal to minus 19. Boy, that looks out of place, doesn't it? Okay. So here we have 4 equations for unknown. We could be solving your GPS right here. 4 equations, 4 pieces of input. You want to try to do that by elimination by addition, by substitution, by graphing? Please say no on graphing. Okay, good. Okay. Have you ever tried to graph a 4-dimensional problem? Don't? Okay. To avoid those at all costs. 3-dimensional stink, but 4-dimensional awful. Where are you going to put it, that 4th dimension? You know, we don't have room for it. Okay. Not in a 3-dimensional universe. So what are you going to do? Second? Did you say augmented matrix? Yes. Let's do it. What would that be? This indicates a matrix is coming on. Oh, and by the way, weren't they nice? Very, very nice. What they did, they lined up all the variables for us. You know, they could have given us just a bunch of equations. They could have even mixed up the variables. They could have started this one with x3 minus 3x4 plus 4x2 plus 2x1 if they wanted to. The same equation is equal to negative 2. They were very nice to us and lined them all up so it makes it easy to do. Guess what? Life is not always nice, you know. Sometimes you'll have your equations all jumbled up. They may not leave spaces where you need spaces and stuff. They did, making it very easy for you. So they made it easy. Do it. What's your augmented matrix? 0, 1, 1, negative 2, negative 3. Got it. Next. 1, 2, negative 1, 0, 2, 2, 4, 1, negative 3, negative 2. 1, negative 4, negative 7, negative 1, negative 19. Got it? All right. What do we do next? What do we want that to look like? Say again? Right, exactly. Is there any way we can get it in that order with this without doing some elementary row operation? No, of course not. What would be your suggestion of what to do first? Second? What do you say to do? Interchange, exactly. Exchange the first 2 rows. a legitimate elementary row operation, make row 1 interchanges with row 2. Exactly. I want to just erase and go, but let's do it out. That would be a 1, 2, minus 1, 0, 2, and a 0, 1, 1, negative 2, negative 3. Try to keep them in line, okay? Just write down the others. See, a lot of the tediousness of this is just having to write all these things down all the time, but you almost have to do it just to keep from making stupid errors. That's why computers are pretty nice to do this. Okay, what next? You got a 1 in the upper left. That's what we wanted. Very good. Next. What's the next thing we want? Once you got that 1 in place, you want, yes, well, the 2 and the 1? Okay, you want those to be zeros. Exactly. You want zeros below that leading 1. Start with that leading 1, deal with it, then go to the next one. Okay? So how would you do it? Negative 2 times row 1, add it to row 3, and that becomes a new row 3. Got it. So let's do it. We're using row 1, so write it down. 1, 2, minus 1, 0, 2. Okay? We're not messing with 2, so write it down. 0, 1, 1, negative 2, negative 3. What's your new row 3? 0. Okay? See what it says. Negative 2 times row 1. We did that here. Negative 2 times row 1 is negative 4 plus 4, 0. Boy, they made this a nice one, didn't they? Okay, I'm liking this already. Next. A little louder. I hear all sorts of grunts and groans, but I can't make out what you're saying. Second? 3. Excellent. Okay? Negative 2 times negative 1 is positive 2 plus 1 is 3. Good, good. Don't like that as well, but it's okay. Next. Negative 3. Okay, that's not bad. Next. That's, what'd you say? Okay, I hear something, but I can't make it out. Which gives you? Okay, let's try it. Negative 2 times 2. Negative 4. Minus 2. Minus 2 minus 4. Minus 4 minus 2 is? What's that? Negative 6. Thank you very much. Okay, very good. It's easy math, but it's tedious. Okay, be careful with it. And by the way, folks, perfect attendance again today. Okay, this class has not failed in 4 meetings to be perfect attendance. Way to go. Keep it up. Okay. Next. Help me, help me. You want that? Okay, we want that in a minute. Let's get these done first. That's why I said, think of yourself as programming in the computer. Cover all the bases here. Cover all the acids if you're in chemistry, but never mind. But where do we go from there? We want that to be a 0 too. How do we make this become a 0? Negative row 1 plus row 4. Got it. Negative row 1 plus row 4 is the new row 4. Okay? So what would that give us? 0, negative 6, negative 6, negative 1, negative what? 21. I'm liking that less and less, okay? All right, what next? We got a 1 here and 0 is below it. Good. What do we want next? The first non-zero entry in the second row we want to be a 1. Guess what? We've already got it. And what do we want next? 0 is below it. We already got a 0 below it. Super. But now we want that to be a 0. So how will we make that happen? Say that again? No, let's not. If you went there, then you're going to bring a -3 down here. See, -3 times that makes -3. Don't want that to happen. Use your 1s. Use those leading 1s. That's why we get them. Multiply 6 times row 2 and add it to row 4. Excellent. 6 row 2 plus row 4. That's going to be the new row 4. I'm going to quit writing that in. Okay. All right. Now we're not using row 1. It's already where we want it, so write it down. 1, 2, minus 1, 0, 2. That's the tedious part here. You just have to write these same things over and over and over, okay? Next, you're using row 2, so don't change it. 0, 1, 1, -2, -3. Row 3 is just like you want it so far. Well, let's not. Let's cheat a little bit. Save a step. Right? Be lazy. All right, now y'all don't know that, do you? Okay, I'll be lazy. What might we do with row 3? You suggested it earlier. You're looking ahead. You were suggesting it. Divide it by 3. Row 3 divided by 3 is going to be the new row 3. So that's going to be 0, 0, 1, -1, -2. That keeps me from writing those first 2 rows over and over and over and over again. So you're going to get that done. Okay, now we'll do what we were starting to do. -6, row 2 plus row 4. What does that give us? 0. Good. 0. Excellent. Second? 0 again. Boy, y'all are living right, or I gave you an easy problem. I'm sure y'all are living right. Okay, next. -13. That doesn't look as good, does it? And then -18 minus 21. What does that give you? Second? -39? Is that what you said? All right. That's not so bad. I was hating those big numbers until I saw, guess what? It's a multiple. That's not going to be too bad. In fact, what's the last thing you got to do? Yes, you got a 1 here, 0 is below it, 1 here, 0 is below it, 1 here, 0 below it, and you want that to be a 1. So how do we get that to happen? Yes, exactly. It's called row echelon form, but we sometimes call it the little step thing. Okay, all right, good deal. Okay, so what do we need? Divide by -13. Watch me do this, okay? Row 4 divided by -13. I'm going to do it right now. And later it'll not make any sense at all. But let's see, divide -13 by -13 and you get 1. Divide -39 by -13 and you get 3. Done. Okay. I was really lazy. Sorry. Not so. Okay. I'm not that sorry. Well, I am pretty sorry. Okay. Let's keep this a minute. I think what I'm going to do is wipe, oops, I thought it was. Evidently it didn't take. Okay. Thought I still had my eraser on. There it is. Okay. I'm going to, just because, so we can compare it, just wipe out that first augmented matrix that we had, just because I need more room. You've got all the paper you want. I only have a little rectangle here. What does that reduced row echelon form matrix tell us? I like to start with the last row because they do back substitution. Start at the end and work your way back. What does it tell us? This column represents X4. And what does that say? X4 equal 3. I like that. Let's do it. X4 equal 3. Okay? Now what? Work our way back. Use the third row. What does that tell us? Say again? What's the third column represent? X3, so that'd be X3 minus okay. All right. Let's write down what it's saying first. That might be helpful because I know I skipped steps before and that may be confusing you. X4 is equal to minus 2, right? But we already know what X4 is, right? So this will be X3 minus 3 is equal to minus 2. See, we just, everywhere you saw X4, an X4, you put in a 3. X3 is equal to 1. Very good. You add 3 to both sides. Now, what does that second row tell us? X2 plus X3 minus 2X4 equal negative 3. So let's plug in what we know. X2 plus 1, which is 6, equal negative 3. Exactly. And what does that tell us? Two. Very good. X2 equal 2. Now, if you need more time, more steps, take as many steps as you need. I just have very little room, so I'm trying to do as much as I can in as little room as I can. And what does that first equation here tell us? X1 minus X3. No, this is a column. That's a column. And that's a 0. You see, that's carried all the way. Okay? Equal 2. So plug in what we know. X1 plus, which is 4, okay, equal 2. So that would be X1 equals, okay, yes, negative 1. Because it would be X plus 3 is equal to 2, so X must be negative 1. So we have our one and only point, 1 point. We could write this as an ordered quadruplet because it's 4 equations, 4 unknowns, and the answer would be negative 1. We've got to find it. 2, 1, 3. Let's see how the book did. Negative 1, 2, 1, 3. Excellent. Height. Okay, never mind. Got it. See how that works? Now, I want to just point out a couple things. Why do we like leading ones? It's really easy to eliminate the things before because what you multiply this by to eliminate the 2 is the opposite of this. And that's going to do it. If you multiply this by to eliminate the 1, the opposite of this, which is that. So that's what makes those leading ones real handy in that respect. But then when you get to this step, here, x4 is equal to 3. x3 is equal to blah, blah, blah. But it's just x3, you know, and all you have to do is fill in the other things you know. x2 equals that, x1 equals that, okay? So it makes it so easy to do your final back substitution. So yeah, we like having those leading ones. They are fun. They are very helpful. And that's what we use to eliminate everything else, unless, of course, you just need to, like we saw an example earlier. Well, we saw it here. We just don't show it here. Right here, how we get that 3 to become a 1 is divide by 3. And, you know, at the very beginning, we exchanged 2 rows. We don't have that down anymore, but that's the first thing we did. So exchanging 2 rows to get that 1 in place, or dividing by something to get the 1 in place, or to get the zeros in place, you use the adding a multiple to it, to another equation. And that other equation, most of the time, is going to have that leading 1 in it. Most of the time. There will be places where you can skip a step and get it to work out a little nicer. Okay. Any questions on that? All right. I don't like that they tell you what's going to come up next, but let's see. Yeah. Okay. Let's clear all that out of the way, and let's do another system. Here it is. And they were very nice to you and set it up prettily for you. x1 minus x2 plus 2x3 is equal to 4. x1 plus x3 is equal to 6. 2x1 minus 3x2 plus 5x3 is equal to 4. And 3x1 plus 2x2 minus x3 is equal to 1. They were very gracious and pleasant and nice to line it all up for you, so it's real easy to see. What's your first step? Say again? Get it into an augmented matrix. And what would that be? 1, negative 1, 2, 4. Right? Next. 1, 0, 1, 6. Next. 2, negative 3, 5, 4. Next. 3, 2, negative 1, 1. What do you want the first thing to be true? Upper left entry, a 1. Yay, we got it. We didn't have to do a thing. What do we want the next few steps to do? Get zeros below that 1. Okay? And how would you do that? Row 2. How would you do it? Okay, say that again. Negative row 1 plus row 2. That will do it. Okay? So that means I'm going to leave row 1 alone. 1 minus 1, 2, 4. Okay? What would your new row 2 be? 0, 1. Second. Negative 1. 2. Okay, very good. All right, what's the next thing you're going to do? Negative 2, row 1, plus row 3. And what will that make us have? 0. Is it? Yeah, negative 1. Sorry, I was 1. Good. Second? Negative 4. Perfect. I don't hear well, sorry. Next. Negative 3, row 1, plus row 4. Okay, what does that give us? 0. Yeah. Okay. Second. 5. Okay. Next. Negative 7. Oh, liking that row. Oh, boy. Next. Negative 11. Oh, what a pretty row. Okay. Now, what do you want to happen next? You got a 1 in the upper left. 0 is below it. Next thing you want is the leading line 0 entry in the second row to be a 1. We got it. Perfect. What do we want to happen after that? We want zeros below that too. So how will we get the 0 below that second leading 1? Second? Okay, yeah. Row 2 plus row 3, right? You're trying to get this to become a 0. If you add those two together, you got it. Yeah, you're doing the row 4 already. So, all right, jump ahead, but, you know, think of your computer programming. You're just doing very regular, repetitive, you know. Yeah, unfortunately, you're doing that. All right, so, yeah, first, you're absolutely right. First row stays the same, 1 minus 1, 2, 4. Second row, because you're using it, it stays the same, 0, 1, negative 1, 2. Now the third row you're changing, it becomes 0. I'm sorry? Right. 0, 0, negative 2. Is that right? Okay. Guess what, team? We can stop right there. Why? Okay, don't let this just carry you away somewhere. What does that mean? 0x1 plus 0x2 plus 0x3 is equal to a negative 2. In what universe is that true? Not ours, okay? You can't have 0 equal negative 2, ever. So don't even do anymore. We get to miss that next row that's so ugly. Because guess what? That can never be true. What does that tell you? This system of equations has no solutions at all. Stop right there. 0 is never equal to negative 2. Now, if that had been zeros all the way across here, you keep on trucking, and then later you'll put that on the bottom. You may still have a solution. But if you get to that 0 is equal to negative 2, that can't happen. Ever. Okay. Now, this is when you have systems of equation, and you're doing reduced row, Gaussian elimination, reduced row S1 form, row S1 form with back substitution. Once you see that, you can stop. It can't happen. So we're done. What did they do? Did they go any? No. Well, they did do one more step. No, they didn't. They stopped right there and said, note that the third row of this matrix consists entirely of zeros except the last entry, and that means this is an inconsistent system. Remember when we introduced those words? Inconsistent system. No solutions. That will never be true. You can't come up with any set of x1s, x2s, and x3s that makes that true. Ever. So you can say no solution is one way to say it, or inconsistent system, which means you have no solutions. Okay. All right. All right. Now, ready to go to the next step. The next step is now moving to Gauss-Jordan elimination. Gauss elimination gets you in the row echelon forms, leading one stepping down, zeros below it. That's row echelon form, Gaussian elimination, back substitution. Gauss-Jordan elimination avoids the back substitution by eliminating the values over your leading one. So you just are left with leading ones in a column, zeros above and below. With Gauss elimination, you apply elementary row operations to a matrix to obtain a row equivalent row echelon form. The second method of elimination, called Gauss-Jordan elimination, after Carl Friedrich Gauss, same Gauss, and Wilhelm Jordan, which I think is a good German name, who came quite a bit later, like generations later from Gauss, he just said, what if we do this? Then that will speed things along. Continues the reduction process until you have a reduced row echelon form. Row echelon forms are ones with zeros below them. Reduced echelon forms are those stair-step ones with zeros above and below them. Okay. So let's go to a new system of equations. X, and they were doing x1s, x2s, x3s. Now they're using x, y, z's. You can use any variables you want to. Subscripts or not, whatever. X minus 2y plus 3z is equal to 9. Okay? Minus x plus 3y is equal to negative 4. Thank you for writing this so neatly for me. And 2x minus 5y plus 5z is equal to 17. They always put one of those in there. In fact, I'm beginning to suspect, and I think I'm true. Yes, yes, yes. This is example 3 all over again. But this time we're going to use Gauss-Jordan elimination, reduce row echelon form, and see what happens. What's the next step? Augmented matrix. What would that be? 1, negative 2, 3, 9. A little louder. Negative 1, 3, 0, negative 4, 2, negative 5, 5, 17. I like that 17, don't you? It's a real nice number. Okay. All right. What do we want to be true about that matrix? A 1 in the upper left, we got it. You didn't have to do any work for it. What do we want next? Zeros below it, just like we've done before. How do we get it? Okay, row 1 plus row 2. That's going to give us our new row 2. So that's going to be, you're using that first row, so write 1, negative 2, 3, 9. Now remember, in Gauss-Jordan and Gauss elimination, we really, once we got that 1 in place, leading entry of 1, that top row never changed. And the back substitution was when we did it. Now it will change, but not yet. Next, do what you told me. 0, 1, 3, 5. Good, good. That works out nicely, doesn't it? What's the next thing you want to happen? The 2 becomes a 0. How do we make that happen? Okay, multiply the top equation by negative 2, the opposite of that, row 1 plus row 3. That should do it, shouldn't it? Okay, and what does that give us? 0. Say that again. Yeah, which is 4. Negative 1. Perfect. Next. Okay. Negative 6 plus 5 is negative 1. Perfect. Next. Second. Oh, you can too. Negative 2 times 9. Negative 18 plus 17 is negative 1. It wasn't that bad, was it? Okay. Now, what do we want to be next? We got our leading 1 on the first row, 0 is below it. Then we go to the second row, first non-zero entry. Yes, it's already a negative, it's already a 1. Yes. But now what do we want? Zeros above and below it. This is Gauss-Jordan elimination. So what do we do to the... Now we are going to change that top row. How are we going to change it? We're using this 1, that leading 1. We use them. That's why we have them. Okay? It'll be 2 row 2 plus row 1. Let's do it. 2 plus row 1. Say again? I can't hear you. Okay. It stays a 1. That's the beauty of it. It never changes that leading 1. That's fantastic. We don't want it to. Next. 0. Next. 6 plus 3 is 9. Okay, next is 19. I'm not liking this too much. These are getting big, ugly numbers, okay? What? Second? No, well, the second row stays the same because that's what we're using. 0, 1, 3, 5. But we're going to change that third row, aren't we? Because we also want 0 below that leading 1. And how do we get that to happen? Second? Row 2 plus row 3. That's so easy. What does that give us? A little louder. 0, 0, 2, 4. All right. Now, notice what we have. First row, first non-zero entry is a 1, 0 is below. Second row, first non-zero entry is a 1, 0 is above and below it. This is Gauss-Jordan elimination. What's the next thing we want to happen? You want the leading non-zero entry to be a 1. How do we make that happen? Divide by 2. So I'll write it over here. Row 3 divided by 2 is going to be the new row 3. And I'm going to be really lazy and do that. Okay? 0 divided by 2 is 0. 0 divided by 2 is 0. 2 divided by 2 is? We're dividing row 2 by 2, row 3 by 2 because we want the leading non-zero entry to be a 1. The only way to make that happen is divide by 2. Right?
It has to be a 0 or?
No, it has to be a 1. We want the leading non-zero entry to be a 1. We have it here, we have it here. We want that to be a 1.
Okay, that's what you're saying.
So we divide by 2. So that makes that a 1 and a 2. Buckle my shoe. Okay. 1, 2. Okay, I was lazy and didn't want to write all those other numbers again. What's the next thing we want to happen? 0's above it. And how are we going to make that happen? For the top row, negative 9, row 3, plus row 1. All right, what does that become then? At 1, 0, second, 0. And let's see what the next number turns out to be. 1. That big old number, got rid of it. What we're going to do next? We want that 3 to become a 0. How do we make that happen? Yeah. By what? Negative 3 times row 3, add it to row 2. And what does that give us? 0, 1, second, 0. Very good. And finally, negative 1. And then write that third row down because we're using it 0, 0, 1, 2. And guess what we got here? What we don't have is back substitution. What we do have is x equal 1, y equal negative 1, z equal 2. Okay? A little more work to eliminate, to do Gauss-Jordan elimination, just getting those zeros above the leading ones, but then no back substitution, just write down your answer. Now, that's as long as you have your ones in a diagonal. If you had to skip a step and stuff like this here, then you are going to have a little back substitution, but it'll be much less than what you had otherwise. We'll see examples of that in a minute. Now, we could go back and check and make sure those answers work. You won't feel like doing that or not. It's up to you. Oh, you lazy things. Okay. We don't have to. We'll look at the book and say, or we could either look back to example 3 and say, that's the solution we got there. Or we could look here at example 7 and say, yeah, look at that. That's the solution they have here too. Good for them. All right. Now they do make a statement here. They don't do the work, but they make a statement here, which is well worth noting. They have pampered you so far. I mean, treated you with kid gloves so far. Made them so easy. Guess what? Life's not like that, okay? You'll run into linear equations that are far worse than this one, but even this one has some drawbacks. Here's what we got. 2x minus 5y plus 5z is equal to 11. No, 17. I can't read. Okay? 3x minus 2y plus 3z is equal to 11. That's where I caught my eye caught. Minus 3x plus 3y is equal to minus 16. Okay. Let's do some mental gymnastics here and not have to write everything down. What do you notice is going to be somewhat problematic with this equation, this system of equations? Say again? You don't have a 1. You got to get that first. How would you get a leading 1? Divide that first one by 2. Imagine you've already written the augmented matrix. But when you do that, what does that first row become? 1 minus 5 halves plus 5 halves, 17 halves. Oh, I can't wait to do the rest of this. It's looking so good. No, it's not. You know, you got fractions. And those fractions are probably going to permeate through the whole problem. And probably get a little messy. But he loves his fractions, I remember. Okay. So we don't mind at all. Now, what I also looked for, especially when I saw these first two coefficients, I was wishing beyond belief that that would come up to be minus 15 maybe, or minus 18. And then I could divide by 3, and then I'd have a 1, switch it around, and then avoid fractions as long as possible, okay? Didn't happen. No matter what you did, you're going to wind up with fractional form. usually halves are easier to work with than thirds. So, but since that produced 3 halves and this only produced 1/3, then I would really still be tempted to do that, to do what I just said. The next one's going to be just 2/3, but so why not deal with that? But guess what? The odds are it's going to wind up with a messy answer anyway. So basically what you try to do is minimize the mess, okay? Try to keep it. So, yes, and it says no matter which order you use, the reduced row echelon form will be the same. So do whatever looks like it's going to work best for you, okay? Now, there's a discovery problem, and some of you don't have your books, so I think I'll write this down. These discovery problems, here's my impression of them so far, having taught from this book a time or two. Basically, they're going to be almost predicting what you're going to do next. Maybe not next immediately, but what you're going to do sometime in the near future. And this is one of those cases. Here's a system of equations. 2x1 plus 3x2 plus 5x3 is equal to 0. Minus 5x1 plus 6x2 minus 17x3 is equal to 0. 7x1 minus 4x2 plus 3x3 is equal to 0. What it says to do, without doing any row operations, explain why that system of linear equations is consistent. What do we mean by consistent? Second? Now, it has at least one solution. Can you look at that and tell me that it has at least one solution? The key here is, what are your constants? All 0. Guess what solution could make that true without doing? Oh yes. What do you get? Yeah, if all of them are zeros. If x1 is equal to 0, x2 equals 0, x3 equals 0, it guarantees those 3 equations are true, right? That only works if you got all zeros there. What we call this is a homogeneous system. We're not there yet. We're going to get there in a page or two probably. With that, you know and what they call that solution is the trivial solution. The trivial solution will work for that every time. If all those are zeros at the end, you know that it's a consistent system. Has at least one solution, there it is, 0, 0, 0. Okay? Now, the question is it the only solution? Then you have to do a lot of your nasty work. Okay? But you know it is a consistent system. All right. Now, here's another thing. I'm going to cheat as much as I can here. Okay. I'm being sort of observant, and I think I must be remembering from an earlier term. 2x1 plus 3x2 plus 5x3 plus 2x4 is equal to 0. Blah, 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 blah. Minus 3x4 is equal to 0. Blah, 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 blah. Plus 13 x4 is equal to 0. Okay. Now, what do you notice about this equation different from most of the others we've done? It has more variables than we do equations. And if you think of that, let's start with the real simple case. If I had an equation like 2x1 is equal to 4, it's going to be a pretty easy equation to solve, right? X has got to equal 2, right? But if I had 2x1 plus 3x2 is equal to 6, does that have a unique solution? No. That forms a straight line. It has an infinite number of solutions. Okay, so here's a generalization. I'm not going to say it's always true, but I think it is. Anytime you have more variables than you have equations, you anticipate having infinite number of solutions. Okay? And that's what this is asking. The following system has more variables than equation. Why does it have an infinite number of solutions? Well, number one on this one, you know a solution, right? 0, the trivial solution. x1 equals 0, x2 equals 0, x3 equals 0, x4 equals 0. So we know it has at least one, but then because you have more equations than variables than you have equations, when you do the row reduction here, you'll never, ever be able to eliminate, get what x4 is. Ever. You might be able to figure out, get ones in the diagonal, okay, and that type of thing, but you'll never be able to do back substitution and get everything. It's going to have an infinite number of solutions. Okay, let's move on to example 8, which I think is sort of going to demonstrate or illustrate that a little bit for us. Okay, the only difference here, this isn't a homogeneous system. Oh, are you trying to tell me we're out of time? Why did you bring up such bad news, huh? Okay. We'll begin next time with example 8. I already have a mark right there. Okay? So we'll go from there. Let me give you a few homework exercises. We almost finished 1.2. We came that close, okay? Do any of the odds 1 through 5. I think I assigned those before. Do either 7 or 9. I think I assigned that before. Do any of the odds 11 through 17. I think I assigned those before. And I think this is where the new ones start off. Any of the odds 19 to 23. Any of the odds 25 to 29. No, 25 to 37. Do 39. I mean, that's a big, long, hairy problem. If you have a software program or graphing utility or something, you might be able to do that. If you don't get too frustrated with it. If you have a graphing calculator, there is a way to do that on it. You'll need to get your handbook, and read and see how to do that. I can't tell you how because I don't know what calculator you have, because different calculators have different input syntaxes and things like that. Okay, and then we were just about to hit on homogeneous systems, so stop there. So you can either stop at 37 or try 39. Stop there, and we'll do the rest of those next time. All right, good deal. And this time, after 2 days in class, I'll say have a good weekend. Usually it's been after 1 class I've been saying that. This time after 2. Have a good weekend. Working linear algebra problems, that'll make it good, right? Yes. Okay. All right. I'll end my